Direct current DC sources and circuits with DC sources do not change direction with time, but voltages and currents that vary with time are very common. The electric mains supply in our homes and offices is a voltage that varies like a sine function with time. Such a voltage is called alternating voltage, and the current driven by it in a circuit is called the alternating current. Today, most of the electrical devices we use requires AC voltage. This is mainly because most of the electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage to DC voltage is that AC voltages can be easily and efficiently converted from one voltage to the other by means of transformers. Further, electrical energy can also be transmitted economically over long distances. AC voltage applied to a resistor. The current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of the instantaneous current values over one complete cycle is 0 and the average current is 0. The fact that the average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electrical energy. Representation of AC current and voltage by rotating vectors, phasors. Representation of AC current and voltage by rotating vectors, phasors. In the animation shows that the voltage and the current phasors and their relationship at time t1 for the case of an AC source connected to a resistor. The projection of voltage and current phasors on vertical axis, that is Vm sine omega t and Im sine omega t respectively, represent the value of voltage and current at that instant. The animation B represents the phasors V and I for the case of a resistor R in the same direction. This is so for all times. This means that the phase angle between the voltage and the current is 0. In order to show phase relationship between voltage and current in an AC circuit, we use the notion of phasors. The analysis of an AC circuit is facilitated by the use of a phasor diagram. A phasor is a vector which rotates about the origin with angular speed omega. AC voltage applied to an inductor. An AC source connected to an inductor. Usually inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. AC voltage applied to a capacitor. An AC source epsilon generating AC voltage V is equal to Vm sine omega t connected to a capacitor only, a purely capacitive AC circuit. When a capacitor is connected to a voltage source in a DC circuit, current will flow for the short time required to charge the capacitor. As charge accumulates on the capacitor plates, the voltage crosses them increases opposing the current. That is, a capacitor in a DC circuit will limit or oppose the current as it changes. When the capacitor is fully charged, the current in the circuit falls to zero. AC voltage applied to a series LCR circuit. A series LCR circuit connected to an AC source epsilon. As usual, we take the voltage of the source to be V is equal to Vm sin omega t. Phasor diagram solution. The amplitude and phase of current for an LCR series circuit using the technique of phasors. But this method of analyzing AC circuits suffers from certain disadvantages. First, the phasor diagram says nothing about the initial condition. One can take any arbitrary value of t and draw different phasors which show the relative angle between different phasors. The solution so obtained is called the steady state solution. This is not a general solution. Analytical solution. The analytical solution for the amplitude and phase of the current in the circuit agrees with that obtained by the technique of phasors. Resonance. The phenomenon of resonance is common among systems that have a tendency to oscillate at a particular frequency. This frequency is called the system's natural frequency. If such a system is driven by an energy source at a frequency that is near the natural frequency, the amplitude of oscillation is found to be large. Resonant circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set. The antenna of a radio accepts signal from any broadcasting stations. LC oscillations. We know that a capacitor and an inductor can store electrical and magnetic energy respectively. When a capacitor is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomenon of electrical oscillations similar to oscillations in mechanical systems. Transformers. It is necessary to change an alternating voltage from one to another for greater or smaller value. This is done with a device called transformer using the principle of mutual induction. Transformers. In transformer, when an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF in it. The value of EMF depends on the number of turns in the secondary. Thus, the transformer may have an efficiency is more than 95%. Thus, IP by IS is equal to Vs by Vp is equal to Ns by Np. But in actual transformer, Small energy losses do occur due to following reasons: flux leakage, resistance of the windings, eddy currents, hysteresis. A transformer consists of two sets of coils, insulated from each other. One of the coils, called the primary coil, has NP turns. The other coil is called the secondary coil. It has NS turns. Often, the primary coil is the input coil and the secondary coil is the output coil of the transformer.